Welcome back to the Data Science and Machine Learning course from the AI Chidai. Today, we are going to perform data analysis activity upon the Stanford Open Policy data. So here are a few topics that we will be covering. Firstly, importing data and data cleaning, datetime indexing and slicing, time series and bar graph generation with Matplotlib library, introducing the search and hit rates as a part of feature engineering and understanding data at better depths, comparing California traffic stops with North Carolina's traffic stops with multiple bar graphs, and correspondingly, search and hit rates in California by race and country using multi-indexing and scatter plots. Firstly, let us try to import data and perform the data cleaning activity. As we are importing the data, here are a few libraries which we commonly use in our data science activities. Firstly, being NumPy for linear algebra, Pandas for data processing and CSV activities, including loading and writing files, and Matplotlib as a part of data visualizing and graphing. Since it's taking time to load data and display the first 5 elements using the df.head function, we will go ahead and try to understand the following steps. So, firstly, what if there arises a situation where you want to remove certain columns from your data frame? To do that activity, you have got your df.drop function in which you can drop certain columns which you feel have no use in your data set. Here too, we have a few columns as such as the stop time, fine-grained location, police department involved, driver age, and what type of search performed upon the driver. After dropping these columns, we are going to drop any rows that have missing values. As we had seen earlier, missing values are nothing but values that have absolutely no value. You have got no zeros or ones under these missing values. So these values, when they are fed into a data analysis or a machine learning algorithm, they cause a lot of problems, which is quite avoidable. Hence, we will be removing the missing values in our data set. Moving on, we are going to set the index to the date column. So traditionally in our Pandas data frames, indexes start from 0, 1, 2, and so on. Here, we do not want the data to be indexed by 0, 1, 2, but rather we would like them to be indexed by the stop date, which is from the earliest stop date to the most recent stop date, which is how we are going to index our data. Moving on, what we are going to do is an interesting activity performed on Pandas datetime functions, which is the Pandas set index. Once we are done set index, we are going to convert the date which is set to the index into a Pandas datetime object. This enables slicing and dicing of our date feature in our data frame much more easier and efficient. Now that we have the data loaded, this is how it looks like. You have the ID, the state name, the stop date, stop time, location, country name, and so on. Now that we have done this, we will be going to perform these corresponding actions which I previously described and visualize the first 5 elements of our resultant data frame using the df.head function. Also, moving ahead, if one would like to understand what columns are present in his or her data frame, the function df.columns.values describes the columns in a very efficient manner. So, what does the data represent in the end? Each row in our data frame represents a single traffic stop by a police officer. The columns give information about the traffic stop like date, location, etc. Next, we move on to datetime indexing and slicing. Now that we have set the index to a datetime index format, we can use more familiar syntax when slicing. The next cell, which is this, presents several ways we can take advantage of datetime slicing. If there are examples you don't understand, you can try forking the GitHub kernel and play around it a lot more. Documentation of Pandas data frame, which is provided here, is also a great reference. So now that we have done it, here is our resultant data frame, which is indexed by the stop date rather than numbers, which are the 0, 1, 2. Now that we have indexed it in a stop date manner, we are going to perform a few activities. First, let us make a copy of our data frame without changing the original data frame. How we do this is we have defined a new data frame called df copy, which is nothing but a copy of our original data frame. First one, we'll take a slice of all police stops from 1/1/2013 to 31st Jan 2013. So I just comment out all this so that these do not interfere with our original activity. So we have it till 31st Jan 2013. So we have all the ones till 31st Jan 2013, which is significant because we have 325,101 rows having this information. Interesting. So next what we are going to do is we're going to see all the police stops between October to December 2013. How we have done this is 2013-10 to 2013-12, which indicates October to December 2013. Since data involved is much larger in volume, this activity is going to take a little bit more time than our previous activity. So we have 1st October 2013 all the way to 31st December 2013, which in total has 948,228 rows of data. So the rest of the activities I shall leave. Okay, this is pretty interesting. So let us take the data which has the stops information which have occurred only on the first day of each month. How we do is we have df index dot day, which stands for 1. It's nothing but the first day of the month. So we have 1st Jan, the information all the way to June 2016, 1st June 2016. So how have we been able to access the day field explicitly? We've been able to do it since we have converted it to a pandas datetime object. Similarly, let us have analyze the day information for the year 2013. Hitting shift enter. The data is going to be slightly voluminous because the information for these first two cells was taking significant time to load. Here we have it. Finally, we have the information for the year 2013 all the way from 1st January 2013 to 31st December 2013. Pretty interesting numbers. Let's now go ahead and see the data for the only Saturdays. Excellent. So here we have the data for Saturdays only. How it has been able to analyze is understand that we are trying to project only for Saturdays. This is not a typical date object. This is your pandas datetime object, which can understand the date to a very fine level. Now that we have mentioned that we have to analyze only Saturdays, it has returned the corresponding data. This is the data for Saturdays only. Notice that the numbers are pretty accurate. So there's no disparity in how it's determining if it's Saturday or not. Okay, we have one small activity remaining, which is defining the index of df copy to the weekday name. This is pretty interesting though. Let us just perform this activity and now we're done. Yes, it is indexed by the stop date as expected. Perfect. Now moving on, let's analyze the time series and bar graphs with Matlab. Since we have set the index to the stop date and converted into a pandas datetime index object, we can do the same, some interesting time series visualizations of the data. Time series allows us to look for trends in the data with respect to time. Let's take a look at the total number of traffic stops made in California over time. So firstly, let's make of number of arrests made in California on each day. So we have just group it by the stop date, aggregated by the count. Okay. Now that we have obtained this time series data, let us take this and build a date time range starting from 23rd to 2013 January 1st. Date range from 1st Jan 2013, and the periods are going to be length and time series. I know you're going to find it pretty difficult to understand these operations, but once we get the visual out, it will be pretty straightforward. So this is the time series graph, which you have taken the counts of stops that have occurred, as mentioned here, and we are plotting it. So the x-axis is the date and the y-axis is the number of stops. Similarly, we have it here in the resultant pandas series. Now, from the time series graph, we see some interesting fluctuations that seem periodic. To investigate further, let us narrow down the time frame of our graph. Do you notice a periodic trend here which goes up and down, again a small spike in this, right? This is a periodic trend across each year. Let us get down and investigate it in much finer detail. First one, let's build a time series graph for the year 2013. So only for 2013, let's take the count of all stops and plot it with a similar fashion, under which we have the title as traffic stops in 2013 with a label in the y-axis as traffic stops per day. Similarly, let us do it only for January 2013 in the same operation. We have in the year 2013, and this is for Jan. This is a pretty interesting pattern is noticed here. This is nothing but the time series where we are grouping all the stop dates and aggregating them by the count. We have constructed time series graphs for 2013 and January 2013. We see that the periodic variations are mostly in what appear to be a weekly basis. It would not be unreasonable to think that cops makes more stops on certain days of the week than others. Let us test that hypothesis by finding the total number of traffic stops made on each day of the week over 2013 and summarize it with a bar graph. Now, firstly, let us break it down into the days of the week 2013. So now you take the Jan 2013 and mention weekdays, and let's determine the number of stops on each weekday. So from Saturday to Wednesday, this is the order of the stops made in ascending order. So hence there is no traditional week format being followed, but we notice that on either Tuesdays or Wednesday, we can also consider Thursday, as all three are having similar numbers. There's a significant number of traffic stops in California. Which means we have a hypothesis that wow, cops in California made 50% more arrests on Tuesday through Thursday compared to Saturday during January of 2013. Why don't we see this trend? Well, let's see if this whole trend holds across the entire data set. Okay, we'll take the entire data set, do the similar operation of getting the number of stops by weekday and plot it out. So now that it's been loading, let's spend some time trying to understand each operation in each time. I presume you folks are pretty acquainted with this line of code. We are trying to get the counts of arrests with respect to stop date. Moving on, we get the weekdays using the index weekday name and define the number of columns as number of stops and the weekday. And let's sort the values by number of stops, which is by default in an ascending order. And here, similarly, we have it for the month January. So this is the traffic stops in California from 2013 onwards. Okay, this is the multiplied by 100K, this number. And we have a massive difference of 50K as we between Sunday and Friday, which points out that an increased number of stops are performed on Fridays, probably a drunken driving stop, for example. Even when examining the entire data set, we still see that most arrests are made during weekdays than on Sundays. As past few cells have shown, Pandas data frames comes with a vast array of tools to manipulate and query data. We can then summarize and visualize our analysis using time series and bar graphs in Matplotlib using very few lines of code. Moving on, let us introduce search rate and hit rate. To determine if there are racial disparities in traffic stops, we utilize two commonly used tests, the benchmark and outcome tests. Simply put, the benchmark tests examine the proportion of stopped cars that are then searched, that is the search rate as broken down by the race. The outcome test then looks at the proportion of searched cars that actually end up having contraband, that is the hit rate, as broken down by race. We would expect that if racial profiling of minorities exists, then minorities would have a higher search rate than their white peers and a lower hit rate than their white peers. However, as discussed by the same Stanford academics who brought you this data set, the benchmark and outcome tests are not rigorous tests of discrimination and can be fooled by the problem of infra-marginality. The infra-marginal problem arises in discrimination testing when different population groups have different underlying probability distributions. As discussed, different signal contributions of the likelihood of possessing contraband for different populations can lead to misleading results from the benchmark and outcome tests. More broadly, it is important as data scientists that we consider external factors. For example, if African Americans in a certain country commit a disproportionate amount of drug crimes, then it might be reasonable that African Americans are stopped at a higher search rate, though the legality of doing so is dubious. Given the sensitive nature of the topic, it would be foolish to draw conclusions from the analysis of this kernel alone. Instead, we simply use this data set as a practice for plotting and analyzing data in Python. First, let us examine the search and hit rates by race for the entirety of California. Let us make a new data frame which has the grouping by the driver race, which aggregates the count of the states the search conducted sum and contraband found sum. We'll define the columns as number of stops, number of searches and number of cases where contraband was found. And here we define hit rate, search rate. The search rate is nothing but the number of searches conducted by the total number of stops into 100, and the hit rate is nothing by the number of contrabands found by the number of search conducted. Okay, now similarly, since we have performed this activity before, let us plot the search rate and hit rate by race for California. So there's a huge disparity in search rate by driver race in California in respect to percentage, and with respect to a hit rate, it does correspond well, but there's a huge disparity between Asian and white hit rate, which means I feel this data set points out the cops are partial towards the Asian and white races. Now, number 5, let's compare the traffic stops in California with that of North Carolina using multiple bar graphs. One interesting line of investigation is to compare search and hit rates between states. Let us compare the search and hit rates between California and North Carolina. So we have obtained the data for North Carolina with respect to search rate and hit rates for the races white, black, Hispanic, and Asian. We'll plot it out here. Okay, now we have figured out that the search rate for Asian is staggeringly low and for blacks is pretty high, whereas for in terms of crimes committed for black, it is pretty low with respect to white and Asian, but Asian it's staggeringly high. Let's plot the search rates for California and North Carolina respectively. Let's get a bit into Matplotlib now. Okay, so firstly we have set the width of each bar as 0.25 and create bars for California using this line of code. We have POS, which is nothing but the list of the range of values, or which is nothing but the position of bars. We have the data race location, Asian, black, Hispanic, and white with search rate and width and color. Similarly, for North Carolina data, we have position of bars. We made it a slightly longer because adding a width field because we want to avoid overlap with search rate. Okay, let's define the X and Y labels, search rate and driver race. Legends at California and North Carolina. Title is comparing search rate in North Carolina and California by driver race. And let's plot the bars. So the search rate is staggeringly low with respect to North Carolina, which means we can draw an inference that the cops in North Carolina are pretty much more strict than the cops in California. So an inference is one of the issues with multiple bar graph is that it is difficult to compare data with large differences in magnitude. After we plot the California and North Carolina traffic stop rates by race, we can clearly see that California police are much less likely to search a car than in North Carolina. However, because the North Carolina search rate is so much higher, it stretches out of the y-axis of the graph, making it difficult to compare racial differences in the California data. For example, is it clear to us that blacks searched more often in North Carolina than other groups? But does that same trend hold in California? If so, to what degree? These type of questions are harder to answer with multiple bar graphs. Let us plot the hit rates for California and North Carolina in a similar fashion. So here we have a very interesting observation. When examining hit rates, we see that California traffic stops have much higher hit rates than North Carolina's. But this should make sense because North Carolina police search more cars in general. For states with a high search rate, we would expect a lower hit rate because there is a lower threshold for searching unless if there are drastic differences in terms of gun and drug crimes between states, a possible underlying variable that isn't considered. We can also see that in both states, searches of Hispanic drivers tends to be much less successful than searches of other drivers. Finally, let's compare the search and hit rates in California by county using multi-indexing and scatter plots. Now, let us examine the search and hit rate by county and race in California. To ensure statistical rigor, we will remove any counties that have found contraband less than 5 times for any racial group over the time frame of our dataset. First, let us analyze the search and hit rate by county for California. We'll group it by county name and driver race by aggregating it to state, the number of states, the search conducted, and the contraband founds. Okay. Similarly, we have the number of stop counts with respect to search conducted and contraband found as our columns. Here, refining the search and hit rates, which is something but the ratio of search conducted by the number of stop counts into 100, and hit rates is number of contraband found by search rate search conducted count into 100. We're going to plot multiple bar graphs now. So for each county and row in the data, we are going to drop the cases where contraband found is lesser than 5 and drop the cases if it's empty. And this is our final data. So Alameda County, the respective driver race, and the stop count. This is a very informative graph with 115 rows. So finally, to examine how racial disparities in search rates for each counties, we plot their search rates for whites against the search rates of minorities in a scatter plot. In each scatter plot, we will plot a 45-degree line, which is where most counties should lie if there is no difference in search rates between whites and minorities. Thus, if a county lies far above the line, it is much more likely to search blacks than whites. So we're going to put a scatter plot now. And here we have the black search rate, the Hispanic search rate, and Asian search rate. The controversy between black BLM and the allegations of racist cops make it difficult to separate political narrative from fact. By using data science and visualizations, we can tease apart the data to find the truth underlying it. Based on the benchmark test, it would seem that most countries lie around the line of equality. Whereas comparing blacks and Hispanics, however, there is one county that lies far away from the pack with much larger search rates and of minorities than white, by a factor of roughly 6 to 5 times respectively. Let us see which county it is. Identify the outlier using the outlier search, and we can use IDX max to search for search rates of blacks, because in every case, the county that is farthest away from the equality line also has this highest search rate for blacks. In both cases, it is Trinity County for both black and Hispanic. Interestingly enough, the same county is an outlier for black and Hispanic search rates. Let us examine scatter plots of the hit rates and for blacks, Hispanics, and Asians, and highlight Trinity County in the scatter plot to see if it is an outlier in hit rates as well. For hit rates, if a county lies far below the equality line, then it may suggest that police are searching minorities too often, as whites would have higher rates and vice versa. So let us plot the same by highlighting the outlier county. So we have white search rate outlier county here. So there are no clear outliers when examining hit rates. We can see that Trinity County has pretty much more equitable hit rates between whites and minorities. Again, it is difficult to draw conclusions about racial discrimination based solely on benchmark and outcome testing. What we can conclude is that the majority of counties have very similar search and hit rates for minorities and whites, except in the case of Trinity County.